Welcome to the Quantum to Cosmic YouTube channel with me, Ollie. Welcome back to this tutorial series on functions. This series is aimed at first year undergraduate university students or those who are just interested. Whether you just need a refresher on these topics or are learning them for the first time, you're in the right place. Today, we are continuing with partial differentiation, looking at implicit functions in relation to partial differentials. So if you're ready to learn, then let's get into it. An implicit function is when we can't write explicitly that y is a function of x. We can't do this. And so what we will have instead is some function, capital F, of both x and y. And if we collected all the terms onto one side to make this capital F function, it means that we'd have this function equaling 0. So in relation to partial differentiation, it means f will not change as x and y change. So we can say the total derivative, df, which equals our partial df by dx, plus our partial df by dy, is also equal to 0. As x and y change, this change in f won't happen. It will always equal 0, so the change is equal to 0. So if we wanted to work out the gradient of our function, we'd use dy by dx. And by rearranging this equation up here, we can find that in terms of f. So that is just going to be minus partial df by dx divided by partial df by dy. We take this term across, so we have the minus sign. We then divide by df by dy, and then bring back the dx onto that side by dividing by on both sides. So we're left with our gradient equaling minus partial df by dx over partial df by dy, and we can rewrite that as that shorthand notation I showed you before, like so. If we use this function as an example, it was actually the function we used when we were talking about implicit functions back in the differentiation section of this topic, and we found out what dy by dx was in another method, but now we can use our partial differentiation method and see if it's the same. So dy by dx, using the equation above, is equal to minus, and then partial df by dx, well, that's going to be 2x sine y plus y, and that minus 1 will become 0. And then on the bottom, we'll have x squared cos y plus x. And if you go back in your notes, if you've been following along, or if you go and check the video, you'll see this is the same result that we got before. If we wanted to look at an implicit function of 3 variables, say f of x, y, and z, and that was equal to 0, that constrains our point x, y, z to a particular surface. Before, when we were doing this for just 2 variables, we would have x and y constrained to a curve, but now this is to a surface. If we wish to, we could rewrite our function f in the following way. We could say x is equal to a function x of y and z, or we could write y is a function of z and x, or finally that z is a function of x and y. So before we had no change in f on this curve where x and y were constrained. Now we have no change in f on the surface. So that will give us our total differential of df equaling partial df by dx plus partial df by dy plus partial df by dz, and that's equal to 0 again. It won't change along that surface. So now, at constant y, so keeping this dy as 0, we can find what dz by dx is at constant 0. So partial dz by dx at constant y is equal to minus partial df by dx over partial df by dz. Similar equations can be found for constant x, and we'd find that partial dz by dy at constant x is equal to minus partial df by dy divided by partial df by dz. And then finally, for z, we'd have partial dy by dx at constant z is equal to minus partial df by dx, and this is the same as we had before, partial df by dy. So we can find three equations for different gradients, and it will be dependent on which variable we're keeping constant for that. So now if we look at an example, which is in thermodynamics, we'll use these partial differentials quite a lot. The equation of state for a gas can be written as this implicit function of pressure, volume and temperature, where temperature is absolute temperature in Kelvin. Only in simple cases, so I'm going to write this in bracket, we can give pressure as a function of volume and temperature. This isn't always the case, but in these simple cases, we can get pressure to equal a function of volume and temperature explicitly. And an example of that would be ideal gas. We have that P equals RT over V, where R is the universal gas constant, which you'll get to when you get to thermodynamics. But you can see here we've given it explicitly as a function of temperature and volume. But that usually won't be the case, and even if it is, using partial derivatives, like we had for our three variable implicit functions, where it produced the surface, we can write that partial dp by dv at constant t times by partial dv by dt at constant p times by partial dt by dp at constant v is equal to -1. And that's an exact thermodynamic identity, and this will be used when you get to thermodynamics, but it's just to show how useful these equations and these partial differentials can be. So as an exercise, I'd like you to just work out where it becomes -1. I'll give you the first one, dp by dv at constant t. It's going to be minus partial df by dv divided by partial df by dp. And then work out what the others are, times them all together, cancelling where they cancel, and it should equal -1. And later on you'll see how that identity becomes extremely useful. Today we've learnt about implicit functions. In the next video we'll be looking at exact differentials. So if you want to learn more, I'll see you in the next one. If you learnt something new or just enjoyed this video, please hit the like button and don't forget to subscribe and tap the notification bell to stay updated on new videos. In the meantime, stay curious and I'll see you in the next one.